Hello everyone, this is Mr. Kaviani, and by the end of this video you should be able to define position, displacement, distance, and distance traveled in a particular frame of reference, distinguish between displacement and distance traveled, and calculate the displacement and distance of an object given its initial position, final position, and the path between the two. In order to describe the motion of an object, you must first be able to describe its position, that is, where it is at any particular time. More precisely, you need to specify its position relative to some scale or origin point. In this case, on the right, we have a professor walking back and forth along a whiteboard, and you can see the marks on the x-axis indicate her position relative to some zero origin all the way at the left. If an object moves relative to a reference frame, for example, if this professor moves to the right relative to the whiteboard, then her position changes. This change in her position is known as displacement. The word displacement implies that an object has moved or has been displaced. We'll represent displacement as a delta, that's the Greek letter delta, meaning a change in x. X is the letter we will use to represent the position of an object. So delta x means the change in an object's position. That is our displacement. That can be represented by taking the final position, the x final, minus the x initial. So if we take the object's final position and subtract where it started from, we'll get the object's change in position, or its displacement. It's important to note that displacement here is a vector, meaning it has magnitude and direction. And in physics, we'll use a positive and a negative sign to indicate the direction. So in the example on the right, if the professor moves from an initial position of 1.5 meters to a final position of the 3.5 meter mark, we can see here that the professor has traveled a positive 2 meters to the right. We could also say 2 meters east if we wanted to be really specific and indicate the direction the professor traveled in. So that would be her displacement, positive 2 meters to the east. Now, although displacement is described in terms of direction, distance is not. The distance an object has traveled can be defined as the total length of the path it traveled between 2 points. So as you see here, if an object were to travel from point A to point C, and then point D along this sort of curvature, and finally end up at point B, the distance it traveled would be essentially adding up all of those individual steps along that path. However, if we look at its displacement, that would just be the straight line between points A and points B. So the blue line here represents the displacement, and that curved path represents an object's distance. So again, it's important to notice that the distance traveled can be greater than the displacement, as you see here. If this person were to just walk from point A to point B in a straight line, they would have traveled a smaller distance than if they took this curved path shown here by points C and points D. So displacement has a direction. So the arrow here in blue, this arrow right here, is the displacement vector showing the direction from A to B. And the distance as well is shown here in red. And so this is the path the object took. The distance does not have a direction. The displacement does. And that's why we represent the displacement with an arrow, where the arrowhead points in the direction that the object is from where it started. Okay, to summarize, let's take a look at an example problem. Let's say we're looking at Thor, and we see Thor walk 6 meters east. He stops for a moment and then turns around and walks 8 meters west. Now, the first question asks, what is Thor's distance traveled? That is, what is the total distance that Thor traveled? Well, if Thor traveled 6 meters to the east, we'll go ahead and show this on our graph here in the bottom right. Let's say I'm going to start right here. So this is my 0 position right here. And then Thor travels 6 meters, 1, 2, 3, 4, 5, 6 to the east, and so I'll draw in that vector right here, like so. Now, if you don't remember your compass directions, they're right here as well. East is to the right. And then Thor stops, so he stops. I'll just show this below. He stops and then travels 8 steps, or 8 meters west. So that'll be 1, 2, 3, 4, 5, 6, 7, 8. And so Thor ends up here, and I'll draw that arrow in here in blue. Okay. So if Thor walked 6 meters east and then 8 meters west, his distance would just be adding up all of those individual journeys. So that would be 6 meters plus 8 meters, which would give us a total of 14 meters. So that would be our distance traveled, just 14 meters. Now, if I'm looking for Thor's displacement, I have to think about where is Thor now compared to where Thor began. And so if I look at this chart, I can see here, this is Thor's final position, right? This is his final position, and this is where Thor started. Now, these are in the same line. I'm showing the blue line one grid below just so you can see them both at the same time. But again, he's walking just in a straight line back and forth. So if I look here, how do I get from the starting position to Thor's ending position? Well, I see that that is going to be 2 meters to the west. So this right here, this is 2 meters west. That is Thor's displacement. That's how far I would have to travel 2 meters and the direction to the west to get from where Thor started to where he ended. Another way that you can show that mathematically, let's call east positive. So we'll say east here is positive, and then we'll say west is negative, okay? So if Thor traveled 6 meters east, we'll call that a positive 6 meters. And then if he traveled 8 meters west, we can call that a negative 8 meters, which would mean that Thor's overall displacement is negative 2 meters. So we could say that his displacement is negative 2 meters, or 2 meters to the left, or 2 meters west, right? All of these are displacements because notice we have a direction. The negative sign indicates the direction, left tells me the direction, west tells me the direction as well. Whereas my distance, right, it had a unit associated with it, but didn't have a direction. So that would be how you calculate distance and displacement for an object traveling in one dimension. This concludes our video on distance and displacement. Please take a look at Canvas for some exercises to apply what you've learned in this video.